good, whether you believe it or not, we're really good at solving linear ordinary differential equations. You know, where everything is, where there are no products of unknowns or unknowns to powers other than 1. So those we know how to solve. And we did a bunch of problems where we actually solved some of those. But unfortunately, not all problems are linear. So since not all problems are linear, instead of jumping out the window when we get a nonlinear problem, we said, well, maybe we can use Taylor's theorem and approximate nonlinear problems by linear problems until we get better at solving nonlinear problems. So we spoke about Taylor's theorem, and that is a way, that's a theorem from calculus which you had, which tells you, and all this that's on Blackboard now, you had it already in previous classes. It basically tells you how to approximate a function in a certain region around a point. So if the point is z0, and in our case z0 is typically the steady state or the initial condition. It's the whatever was happening at the initial condition. If we know the values at the initial condition, then in a certain region close to the initial condition, called the radius of convergence, we can write the value of the function at another point as an infinite series in terms of the value of the function, all of its derivatives at c0. Now, of course, in this class, we don't want to keep all the derivatives. What we want to do is approximate it just by the first derivative, because that's going to give us a linear function. Notice, first derivative is evaluated as at a point, so it's a constant, multiplied by c minus c0. Not to any power, it's to the first power, so that's the linear. So we don't want to go to the second power, because that would be quadratic. So in a one-dimensional problem where I have only one thing that changes, that means f of x is f of x0 plus the derivative at x0. So these are both constants times x minus x0. This is linear. For a two-dimensional problem where I have two things changing, x and y, that says f of xy is f of x0, y0. So the value, say, of the initial condition, which presumably is known, plus the derivative evaluating the initial condition, also constant. This is df dx, this is df dy. Both constants because they're evaluated somewhere, times x minus x0 times y minus y0. Notice that not only are these to the first power, so they're linear, but also the change in x and the change in y can be in different terms. So they add. So the nice thing about the linear approximation is when two things are changing, they appear in different terms, and the change in x adds to the change in y. Now, if it's a really nonlinear problem, that's not true. This is an approximation. But in this approximation, things are kind of nice. They work like this. We'll do some examples. And this is just a reminder of the solution of linear first-order differential equations, because when we start out with a nonlinear first-order differential equation, and we use Taylor's theorem and chop it off after the linear term, then we adapt to linear equations, which is what we like. Are there any questions on that? Okay, so let's do an example. So let's say we have a CSTR. Again, if there's anything you don't understand that I'm saying, stop me. I don't mind. I want you to learn the material, and that means if there's something you're missing while I'm talking, ask me. So let's have a CSTR, and I have a CA in, and of course, because this is a CSTR, the CA in the reactor is equal to the CA coming out of the reactor. I'm going to presume that I have a volumetric flow rate, a certain volume. Those aren't changing. And I have a reaction, A goes to B. But now I want 2A to go to B, not A goes to B, with a rate constant. So dCA, so the rate of reaction is minus 2K CA squared. It's mass action. Now, it's minus because I'm completing A. It goes to CA squared because this is mass action, so it goes to the square. and each unit of reaction kills off two A's. So that's why I put the 2 here. Now it's a convention. Since K is a constant, you can always lump the 2 into the K if you want to. I don't like to do that because when I want to write RB, that also is going to go as CA squared. But it's a plus because I'm making B, and every unit of reaction makes 1B. So here I would have a +1, and that way I have the same K for both. Each unit of reaction makes 1B plus 1 and depletes 2 A's, -2. So I like to put the stoichiometric coefficient, if it's on the right with a plus sign, if it's on the left of the arrow with a minus sign, explicitly here, and that way there's no ambiguity as to what K is. But you don't have to do that. You can always lump the 2 into the K, and then you would need a 1/2 K here. Okay, so this is the CSTR, and this is nonlinear. This is not linear. So let's write out the CSTR equation. So if we write out the CSTR equation, I've got, and I'm going to assume constant density. And uniform density. And we're given that CA in goes through a step change at t is equal to 0. And so this is an assumed, this is a given, and we want to find CA of t. And we're also given that at t is equal, for t less than 0, the system's at steady state. So this was CA for t less than 0, it's already was at steady state. And the question is, what happens here? Is that clear what the problem statement is? Okay, so let's write out the CSTR equation. So that's dCA dt, because it's constant density, is equal to CA in for t greater than 0. And let's do this for t greater than 0. Minus CA, which is the same as CA, divided by tau. Tau is the volume of the bimicrophone ray. Minus 2K CA squared. Because I have to subtract out, I have to add the rate of production of A. And it's being depleted, so it's minus 2K CA squared. And now what I want to do is before and notice this is nonlinear, so I want to linearize. So I need to write CA squared. And here I'm going to need some help from you to make sure that you're following. Okay, so this is only one variable. So I have f of CA is CA squared. So what is f of x0? If x0 is the initial condition, CA naught squared. Okay, and what's the derivative of CA squared with respect to CA? Higher mathematics? Somebody loud. 2CA. So let's take the K along for the ride, and then I get 2CA. I don't like calling it at 0. I like to do it as t less than 0. Okay, and that's the derivative times CA minus CA of t less than 0. So now I'm sorry for the bulky notation, but when I write CA0, I find that confusing. You never quite know what that is. So here it's clear, I'm talking about CA for t less than 0. So let's plug that in here. I have dCA dt plus CA equals CA in t less than 0 minus CA over tau minus CA t less than 0 squared minus 4k CA t less than 0 times CA minus CA t less than 0. And now what I want to do is I want to write out the same equation for t is equal to 0 when it was in steady state. So let's write out the same equation when it was in steady state. So this is d dt of CA t less than 0. But it was steady state, so this thing is 0. I know this is 0 because I'm given that it was steady state. But just for fun, let's write it out. So this was CA in, I'm sorry, this is t greater than 0, not t less than 0. CA in for t less than 0 minus CA t less than 0 divided by tau. And now here I have minus, okay, I left something out here. This was not CA squared, it was minus 2k CA squared. So I left out the 2k here. So now I have minus 2k. I just write this whole thing, CA of t less than 0 squared. So what did I do? This is the exact equation. This is, for t greater than 0, the linearized equation. And this is the exact equation for t less than 0. And you might say, who cares? Why did I write that? I write that because I want to subtract the linearized equation for t greater than 0 minus the exact equation for t less than 0. And let's see why I do that. The first thing I notice is I have ddt of CA minus CA of t less than 0. So I'm going to define any variable greater than 0 minus the same variable at less than 0 as the variable with a prime on it. So I'm going to call this thing dCA prime dt, where CA prime, anything prime, is defined as that anything for t greater than 0 minus that anything for t less than 0. So anything prime is its value greater than 0 minus the value less than 0. So here, this is greater than 0, this is less than 0. And notice this is CA in greater than 0 minus CA in less than 0. This is CA in prime. This is CA minus greater than 0 minus less than 0. So it's minus CA prime over tau. But the nice thing is this term and this term cancel. They're gone because they're exactly the same. And what I'm left with here is 4k CA t less than 0 times CA greater than 0 minus CA less than 0. That's a CA prime. Is that clear, what I did? So I introduced the prime variables, and all the unprimed variables disappear. And now, I don't have any extra terms. Notice over here I had extra terms. Here I don't have any extra terms. So now I can bring this term and this term together beside the equation. dCA prime dt plus CA prime times 1 over tau plus 4k CA of t less than 0 is equal to CA in prime over tau. So I just brought these two terms to the other side of the equation. And just as we did in the past, I can call this thing 1 over t, where t is the time constant. And I'm left with my usual equation, dCA prime dt plus CA prime over t is equal to CA in prime over tau. It's the usual form of the equation, but with primes, not with unprimed variables. And this is exactly in this form. And in particular, t and tau, 1 over t is a, and b is CA in prime over tau. they look like constants. They're constants, because CA in prime is just a constant. It went from CA in prime is this number minus this number. It's a constant. So both A and B are constants. So I know on board 2 that CA prime of P is just equal to, I can read it off here. It's CA prime of T1, in this case CA prime of 0. CA prime of 0, there hasn't been a jump yet. So CA prime of 0 is 0. The nice thing about the prime variable is the prime variable at 0, or at the initial condition, is always equal to 0. So this term doesn't even contribute to CA prime. It contributes to CA, not to CA prime. And then I'm left with B over A, which is CA in prime. B over A, so it's T over tau, times 1 minus e to the minus T over B. So, and if I want to get CA prime, CA of B, well, CA is just CA prime plus the initial condition. So that's CA of T less than 0 plus CA in prime is dealt with CA in. T equals to tau, 1 minus e to the minus T over tau over BT. And, okay, so, or actually I'm usually writing like this. And let's see what this curve looks like over here. So now we know what this looks like. This thing looks like what it was before, so this value, plus something times 1 minus an exponential. And that's the linearized solution. A linearized solution. But let's think for a minute, how does the linearized solution differ from the real solution? So let's recall that we approximated CA squared versus CA. We know that CA squared versus CA looks like this. And we approximated it by a linearized function around CA, around the initial condition. And we approximated it by a straight line. So notice, since the function curves upwards, called convex, that the linear approximation is always smaller than or equal to the function. So that says, since the rate of reaction goes as CA squared, that when we approximate the white curve by the pink curve, we're underestimating CA. So we're underestimating the rate of reaction. So really the rate of reaction is a little faster than we're estimating. Hopefully there isn't a big difference, but it's a little, so that tells me that the actual solution, if we could solve the nonlinear equation, would have a little less CA in it because we underestimated the rate at which we're killing it. So the real nonlinear, even though we can't solve for it, we know it's going to be a little less. Nonlinear. But notice that initially, when I'm close to here, there's very little difference. The further I get from CA0, close to CA at t is equal to 0, the linear approximation is really good. And the further away I get, the worse it gets. Is that clear? Okay, so that's one example of using a linearization in such a problem. Any questions on that? Questions? So it looks kind of easy, doesn't it? Looks easy. Just Taylor. Just thank Mr. Taylor. Let's do another one. Another easy one. Let's say I have a tank. And I have fluid coming in, and I have fluid coming out. And I'm interested in the level. Yeah. And, okay, so I would like to look at the change in volume in the reactor. So I have a cross-sectional area A. So dET of AL, the volume in the reactor, is equal to, and A is a constant and L is can be a function of time, is equal to the flow rate in, the volume in. That's V in minus V out. If I were interested in mass, I would have rows, a row here, and row here. And if the row changes with time, I would have to include that in here. Or if the row in were different from the row out, I'd have to include that. But I'm going to assume that the rows are all uniform and constant, so I don't have to worry about that. So right now, and let's say we're given that for t less than 0, L is at steady state. And V in undergoes a step change from V in less than 0 to V in t greater than 0. And I want to find L of t. Is that clear what the problem statement is or the question is? Okay. So what is known and what is unknown? Well, A is known. V in is given. L of t is unknown. And V out is unknown. So I have two unknowns, but I only have one equation. So my degrees of freedom, the number of unknowns minus the number of equations, is 1. So I need another equation. So to get another equation, I need to relate another equation, and let's try to relate the out to L. And that would be a second equation. A long time ago, speaking of need another equation, a long time ago there was a very sad incident that happened, that the space shuttle, the Challenger, was launched from Florida. This was, I think, in the late 80s, and it exploded. And there were a lot of tasteless jokes that went around at the time. And one of them was, what does NASA stand for? And the answer was, need another 7 astronauts. So here we need, this is not as tasteless, we just need another equation as opposed to 7 astronauts. Okay, so how do I come up with that? Well, let's reach back to your unit operations class. In your unit operations class, there was one equation that kept coming up all the time from Mr. Bernoulli. Actually, it was a whole family of Bernoullis. There were 3 of them. But in Bernoulli's equation, we had, so let's compare this point and this point. So in Bernoulli, we had P0 plus rho GH plus 1/2 rho U squared was the same at all different points. So that was basically one form of Bernoulli's equation when you don't have too much else going on. So P0 is atmospheric pressure. So let's compare point 1 and point 2. So comparing one and 2, we have P0 plus rho G L plus, and over here, I'm going to assume the velocity, because A is so much bigger than the area here, I'm going to ignore the velocity. Because L moves so slow. So it's 1/2 rho times 0 squared. So this is at point 1. And at point 2, point 1 at point 2, I've got P0 plus rho g times 0. Because the height here I'm defining is 0. Plus 1/2 rho times u squared, which is velocity at the outlet, u2 squared. Okay, so let's cross out the zeros, and let's cross out the P0, and let's cross out a rho, and I have that u2 is equal to root 2gl. And that's U2. How about the outlet volumetric flow rate? Well, I'm going to have some sort of A2 here. Is some cross-section area. So V out is equal to A out. U2 is equal to A out times root 2GL. And I'm going to lump all this stuff into a constant K, because there could be some irregularities, so the constant may not be exactly out. But the point of the matter here is I can say V out is equal to, let's use a little k, it's easier to make, K square root of L. So V out goes as K times the square root of L. Is that clear? It's unit numbers. So this now is the equation I was missing, because it relates V out to L of T. And clearly, the higher the head, the more it comes out, but then it goes as the square root of L and not linear root being L. Unfortunately, this is not linear. So we need to linearize the square root of L. So let's linearize the L. So I have root L is equal to, again, I have this situation. So I need at steady state, so what is, if the function is the square root, what is this term then? If this f of x is the square root of L, what is f of x 0? Do I have to start calling on people? This is just seeing if you're awake. This is not even requiring thinking. Okay, I'll count to 3. If I don't hear, I'll call on people. 1, 2, 3. Okay, why don't we start back over there? If f of x is the square root of L, what is f of x 0?
1/2 L 0.
1/2? Why is it 1/2? Square root of L 0. Where L0 in this case is L at t less than 0. Okay, so now I have to take the derivative. What's the derivative of the square root? 1/2 square root. Times L of t minus L of t less than 0. And this is now linear because L of t0 is t less than 0 is a constant. This is the only variable, L of t. So now I can plug this expression into here and this expression into here. So let's do it one thing at a time. So I have A, the exact equation. A, the L dt is equal to V in t greater than 0 minus V out. V out is K square root of L t greater than 0. Actually, I'll just call it L. Instead of calling it here. And now I linearize. So I've got A, the L dt plus V in equals V in t greater than 0. Minus k times, and now for the square root of L, I write the square root of L t less than 0. Plus 1 over 2 square root of L t less than 0 times L minus L t less than 0. Is that clear? All I did, I took the exact equation and I plugged this in for the square root of L. So this is the linearized equation. Now I look at the t less than 0 exact equation, just as I did in the other problem. Well, the t less than 0 exact equation is a dl dt is equal to v in at t less than 0, this is just t less than 0, minus k times the square root of L t less than 0. It's the exact same thing as this, just with t less than 0. And now I subtract these two, and this is t less than 0. Now this was at steady state, so this thing is 0. So I subtract and I get, this happens to be 0 because it's steady state. But I subtract and I get a dl prime dt, because then L minus Lt less than 0 is equal to v in t greater than 0 minus v in t less than 0, v in prime. And again, this term cancels. It's exactly the same. So all I'm left with is k over 2 root L t less than 0 times L minus L t less than 0 is L prime. And notice that, again, this gives me, I can divide through by a, get rid of this. And now I have L prime dt plus k over 2 root L of t less than 0 divided by a. L prime is equal to v in prime over a. This is exactly of the form we always have. It's exactly of this form again. Where a of t, I have a time constant here. This is 1 over t. Time constant is, this is 1 over the time constant. And this is just b of t. And again, v in prime is just a constant. So both a and b are constants. And so therefore I have L prime of t from this equation. And again, the prime variable at 0 is 0, because the prime variable at 0 is before the jump. So it's what happened less than 0 minus at 0. So there's no change. So this is just equal to b over a times t, b over a, times 1 minus e to the minus t over t. Where, again, what happens now? v t, here L versus t. I had a steady state value, and now when I do the linearized problem, I get it looks like this. And now the question is the nonlinear problem higher or lower? So let's think for a second. The square root of t, the square root of L versus L, is a concave function, not a convex function. Convex goes up, and we call this concave because it looks like a cave. It looks like you're in a cave. So when I approximate this by a straight line, notice the straight line is always above the real value. So that says I'm overestimating the square root of L. I'm overestimating this, so I'm overestimating V out. So that means V out is really less than I think. So if V out is less than I think, that means L is going to be higher than I think. So it says the real value of L is going to be a little bigger. Nonlinear linear. Now, let's just go back and think for a second. Over here, in this case, when we had a first order reaction, well, actually before that, when I go back to this, let's just, what I didn't tell you is what is Kp? Kp is the steady state gain. It's the change in the output at steady state over the change in the input steady state. So that's equal to delta Ca steady over delta Ca in steady. So this is delta Ca, this is delta Ca in. And then t goes to infinity at steady state, the exponential drops out, and I just get big T over little t. So this is big T over little t, big T over tau. Which in this case, over here, tau, big T, was this. So I need a little more Blackwood space. So big T, so this is 1 plus 4k. Big T. So big T is tau divided by 1 plus 4k Ca of t less than 0. Tau divided by tau. So you can see that Kp in this case is 1 over 1 plus 4 k Ca of t less than 0. So in this case, the steady state gain is this value. So notice this value is less than 1. It's less than 1, so that says the change in Ca is smaller than the change in Ca. And if you recall, if for a first order reaction, when we didn't have a second order reaction, but we had a first order reaction, recall for A goes to B, the steady state gain, Kp is also T over tau. And it was 1 over 1 plus K tau. So I want to compare the current second order linearized case, Kp, to the first order Kp. Notice that the first order Kp doesn't depend on the initial condition. The change in Ca steady state over the change in Ca in doesn't depend on the initial condition. It's 1 over 1 plus k tau. The difference here, when we have a linearization, the Kp depends on the initial condition. Whenever, and it's a feature of linear equations, an unusual feature, that the change of the out over the change in the in doesn't depend on the input. That's only true for first order systems. For any nonlinear system, even when you linearize it, the fractional change in the out over the fractional change in the in, change in the out over change in the in, always depends on the initial condition. So what that tells me is if I had a different steady state to begin with, if I had a different Ca in to start with, rather than this one, once I start down here, then Kp would be different in this case. But it wouldn't be different in this case, in the first order case. Let's calculate Kp here. Yep.
Before you continue, will you go over the general solution for L prime again in 1
Can you speak slower?
Sorry. Will you go over the general solution for L prime again?
That's what I was just about to do.
And where the first term is 0?
Oh, okay, sure. This is not just in this problem, this is in any problem, is that when I define a prime variable, it's the variable minus the variable before I started. So at t is equal to 0, that's before I started. So The prime variable at 0 is its value before I start minus the value before I start. So it's the same thing. So that's identically 0. Okay? And that's not just this problem, that's the definition of a prime variable. So again, here the solution is this, and if I want KP, that's L prime of P, that's L prime of infinity over V in prime. So it's the change in the output at infinite steady, hopefully I use steady state, minus V in prime, because V in prime is just a step function, so it's the same at all times greater than 0. So that's just equal to, when t goes to infinity, this drops out. So I have just t over a. Which reminds me, we need a TA for this class. And I negotiated with somebody on Friday, and I'm hoping she will say yes. That wasn't planned. I just saw the T and the A, so I figured I should do that. And you know what T is. T was somewhere. Oh, T is the, give me T. Here's T. So T over A is just K over 2 root L of T less than 0. So that's my KP. Are there any questions on anything we've done so far today? Not just what's on the web, not just what I just did to say. Any other questions? Yep. Okay, when you wear the mask, you have to talk loud and slowly. Otherwise, all I hear is.
Okay, I just want to make sure I understand that last line
That came from here. So to get KP, it's the change in the output. L prime is the change in the output over the change in the input, V in prime. So that's big T over A times 1 minus this, but at steady state, when little t goes to infinity. When little t goes to infinity, this is 0. So I just have T over A. And then I look back here, what was T? And T is the inverse of this, so I have it upside down. So maybe I can get it right this time. So that's 2 root L of T less than 0 divided by K. And when I multiply by A, when I turn it upside down, A is in the numerator, so I divide by A, A's cancel, and I just get this. Good thing you asked the question there, because I had it wrong. Other questions? Okay, so notice that everything we've done so far, we've only used this one. So I'm going to use this one, because we need practice in this one, 2 dimensions. That is, so far there's only been one thing changing. Maybe 2 things changing. So what we're going to do here is look at another example of a CSDR heat exchange. With no reaction. Because if we put a reaction in, then the problem might actually be interesting, and we want to make sure that nothing is interesting in this question. But we want to start with the easy case, and we'll make it interesting later. We start out with the boring case that you can solve easily, and then you make it interesting later. Okay, so what is a CSDR heat exchange? So I've got a good old CSDR. I've got something coming in, something going out. I have no reaction, so that's unfortunate. And then I have coil, where I've got VC in and VC out. C meaning the cooling fluid. And I've got TC in and TC out. Now I'm going to presume that VC in and VC out are the same. So they're just going to be VC. I'm going to make it equal because I'm going to assume that the cooling fluid doesn't boil. It's constant density. So I'm assuming, first thing I'm assuming, is that VC in equals VC out, which is VC. So I don't need in or out. So that's constant density. And now I have some T in and some T. And again, because it's a CSTR, I don't need an out, because what's in the reactor and what's coming out are the same. And let's picture what's going on. So I've got fluid coming in at one temperature. I've got coolant fluid going through the coil. So it's coming in hot. I'm cooling it, and then it's coming out cooler at the output. Nothing particularly exciting. So why don't we see exactly, let's see if I left anything out. No, I think I have everything I want. I just probably should know that I have a V in here. I'm also going to assume that V in equals V out. That is, I've got what's coming in. If it doesn't have a C, it's coming into the reactor. If it has a C, it's coming into the coil. So why don't we write out what we're interested in is assume that there's a step change already given. That VC, I use a superscript, versus T undergoes a step change. And for T less than 0, the system is at steady state. And I want to find T of D. Sounds straightforward enough. Let's see if I left anything. Yeah. Okay. Clear what the question is? So let's, I want to be T of T. So what sort of balance do I need to do for the temperature? And let's not call it temperature because I use T for time constant. Theta. 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 I want to reserve capital T. I'm going to reserve capital T for time constant. So temperature is theta. Okay, so what balance do I need if I'm interested in the temperature? Energy balance. So I have du dt is equal to H in minus H out plus Q, where I'm not going to worry about the work. So I'm going to assume that the work is negligible. So this is going to be rho V C V d theta dt is equal to, and this is volume, rho V Cp. So I'm also going to assume Cp is equal to Cp times T in, theta in, minus theta ref, for some reference, minus rho V Cp theta minus theta reference, plus Q. And let's cancel the rows. CV is CP, so I can cancel those. Actually, I shouldn't do that because I still have Q. Let's not cancel anything. Okay, so next. So, great. We had one unknown, which is T. Theta. One unknown, which is theta. And we wrote out an equation where not only is theta unknown, but Q is unknown. So I need another equation for Q, because I just added a new unknown. Well, one way of getting an equation for Q is to do a heat balance on the coil. So this is a heat balance on reactor. Now to get Q, I'm going to do a heat balance on the coil. And that's going to look pretty similar, except I'm going to have a rho C VC CVC d theta c dv is equal to rho c vc cpc theta c in minus theta c left minus rho c vc cpc theta c out minus theta c left minus Q, because the Q that goes from the coil into the fluid heats up the fluid. It takes heat from the coil to the fluid. So it's plus in this direction, but it's negative. It's plus for the reactor and it's negative for the coil. Is that clear? And what I'm going to assume is that the coil is a lot faster than reacts a lot faster than the reactor. The reactor is really big. The coil is really thin. So it reaches a steady state much, much faster than the whole reactor. So I'm going to assume that the coil is pseudo-steady. Have you had pseudo-steady state in your reaction engineering class yet? Or quasi-steady state? The idea is the following. Let's say you're in the jungle in Africa and there's an elephant. And there are a lot of little fleas on the elephant. So the elephant lumbers. Every time the elephant makes a move, the fleas are a lot faster. And they reorganize in a steady state distribution long before the elephant has put his foot down. So the fleas reorganize. They're almost always at the instantaneous steady state consistent with the instantaneous position of the elephant. So that's the idea of pseudo-steady state, is that the flea distribution equilibrates much faster than anything that the elephant can do. So the idea here is that the coil equilibrates, the coil of the fleas, and the reactor is the elephant. So that's the pseudo-steady state assumption. You do that in kinetics all the time when you have reactions with very high rate constants and others with very low rate constants. So the ones with the big rate constants reach steady state much fast, almost reach steady state before anything's changed in the slow variables. So you get fast variables and slow variables. So what that means is I'm going to ignore the d's theta c dt. The theta c refs cancel. Actually, they cancel here as well. And I get an expression for Q. And I have that Q equals from here. Rho C VC CPC times theta C in minus theta C out. And now you might say, great, this equation had one quantity I didn't know, the size thing, it had Q. So now I came up with an equation for Q, but that didn't help much because now I've got a new thing I don't know, theta C out. So I need another equation for theta C out. Is that clear? Because I've just taken a new equation that introduces a new unknown. So now I've got three unknowns. I've got Q, theta, Q, and theta C out, but I only have two equations. So I need a third equation. So this is not like your shell and tube heat exchanger, where you know that the answer is UA delta T log mean from your unit ops class. Because there's no shell, there's just this thing. And because that's really nonlinear, a logarithm. So let's see what we can do here. So we need a new equation to relate Q to theta C out. And we just have to go back to first principles. That's always the best, is go back to first principles. So what's Q? Q is the integral. So let's think of the of this guy, the coil. If it has if the diameter of the coil is much smaller than the radius of the radius of curvature of the coil. So the radius of curvature is like this, and the coil is only this thin. So if we look locally, the coil looks straight. It doesn't see the curvature. So then I can integrate from 0 to L, where L is the length of the coil. Of some sort of U, a heat transfer coefficient, times the area. So I'm doing a balance on a piece of coil. And here I have X in this direction, and I'll call the radius A, little a. So, and the length is L of coil. So I'm integrating from 0 to L of U times the area. So let's go balance on a small piece. So this is dx. So the area is 2 pi a dx. That's the area, UA, times delta t. So the delta t is t at x, theta at x, minus the outside temperature. The outside temperature, and this is theta c of x. The outside temperature is just theta. And theta of the tank. And theta of the tank is just a number right now. It's whatever theta is. Is that clear? So if I want to get the total heat transfer from the coil to the tank, because I've written it as a plus sign when it goes to the tank, then that's the U times the area, 2 pi a dx, times the temperature in the coil minus the temperature of the tank. The temperature of the coil varies with X. The temperature of the tank doesn't vary with position, it only varies with time. Is that clear? Okay, so now, of course, this is not a trivial problem, but I really have to figure out what theta c of x is and then integrate it. I'm going to be lazy here and say, when I integrate something, let's multiply and divide by L. If I multiply and divide by L, I have multiply by L here, and if it divide by L, and this becomes the x over L, this just becomes 1. The x over L. I change variables from x to x over L. So this thing is the area. And when I integrate something from 0 to 1, well, why don't we say, actually, I can leave it the way it was before. I don't even have to do that. Let's leave it the way it was. So when I integrate from 0 to L, 0 to L dx of something, and I divide it by, so I'm going to multiply by L, but I'm going to divide by the integral from 0 to L dx. So this is still A. But so I have UA, and I have the integral from 0 to L of something divided by the integral from 0 to L of 1. So this is like adding up. This integral is like adding up all the students in the class. And this is like the grade of each student in the class. So I add up each student in the class times that student's grade, and I divide by the sum of the total number of students. What do I get when I do that? If I get the mean. So this is an average. This thing's like an average. So Q is UA times the average of theta c of x minus theta over the coil. The average of that. And I'm going to approximate that average in a very simple-minded, arguably dumb way. So it's going to be UA. I'm going to assume that the average, and this is not a great assumption, but it's the one we're going to be stuck with, it's going to be the value at 0 plus the value at L over 2. The average of the input and the output. Is that the right answer? No. But it's a crude approximation, and it's linear. So I'm going to take 1/2 of theta c of 0, which is theta c in. Let's in on the bottom, minus theta, plus theta c out, minus theta. So it's the average of theta c minus theta, which is just, in this dumb approximation, 1/2 the value of the inlet minus 1/2 the value of the outlet. So let's just rewrite that. That's equal to Q is equal to UA times theta C in plus theta C out over 2 minus theta, because I've got minus 2 theta over 2. Okay? Now I have 3 equations and 3 unknowns. I've got equation 1, I've got equation 2, and I've got equation 3. 3 equations and 3 unknowns. And so now I want to combine this one and this one and get rid of theta c out. Once I get rid of theta c out, I have Q in terms of things I know. Theta c in and UA. And of course the unknown, theta. And then I'll take that value for Q and I'll plug it in here. So that's where I'm going. Just before I get there, I want to let you know where I'm going. Let's just see if I left anything out there. Okay, so I have this thing, it's always in my way. But let's rewrite this equation. This equation is theta c out is equal to, I've got Q over rho C VC CPC. And so I divide this out. And I need to subtract that from theta c in. Yes. So I just solved for theta c out here. And I do that, so now I can put theta c out into here. So I have Q is equal to UA times theta c in plus theta c out. Theta c in plus theta c out. Well, theta c out is theta c, another theta c in, 2 theta c in, minus Q over rho C VC CPC. And then I have a minus theta. So again, I solved for theta c out here. I got this. And now I plugged it into here to get Q is UA theta c in. And now for theta c out, I have another theta c in. So 2 theta c ins divided by 2 is 1. And then I have minus Q rho C VC CPC, and I have a 2 here from here. And then I have a minus theta. Is that clear? Just algebra. Hopefully I haven't made too many mistakes, because I never have the algebra in my notes. Okay, so now I've got Q on the right and Q on the right, Q on the left. So let's solve for Q. So Q is equal to UA theta C in minus theta divided by 1 plus UA over 2 rho C VC CPC. So I brought this to the other side of the equation, factored out the Q and divided it out. And just for fun, I'm going to multiply top and bottom by VC. Just for fun. So I don't have a VC here, but I have a VC here. And this is Q. And now I'm ready to plug Q into here. The only thing is, what is U? the overall heat transfer coefficient. What is that? Where did that come from? Did a little birdie tell me what that was? Well, it turns out the heat transfer coefficient depends on how much turbulence I have in the coil. And the higher the velocity of the fluid in the coil, the more turbulence I have, and the higher the better heat transfer coefficient. So in this case, with a coil, to treat U as just a constant isn't right. So it turns out people have done studies, and they've just come up with a correlation. And the correlation they have is that U can be very well correlated. Should I say U or UA? So I don't have to carry it around. UA. A is just a constant, so no need to carry it around. Can usually be written as A, B, C to the B, where B is between 0 and 1. So it goes up with VC at some power less than 1. So that says I can rewrite this as Q is equal to A VC to the B plus 1, because I have a V here, over VC plus A VC to the B over 2 rho C CPC times theta C in minus theta. And now we're ready to solve the problem. Are there any questions? Yeah? Yes. Little a's and big A's are different. Little a and little b are values that came from a correlation, which I'm not going to bother you with the actual numbers right now. The a is just some coefficient. And of course, the a is proportional to the area of the coil. Even if the coil is area 1, it's going to be a value for a. Do we have a picture of one of these blackboards so I can do some erasing? Yeah. Someone take a picture of blackboard 2. That's the one I want to erase. You got it already? Okay, thank you. Okay, so I want you to notice here that Q depends on VC and theta C and theta. So let's notice what happens in this problem. We said that VC in, is it VC? Yeah, VC. Or VC is going to change can I bother with a name? No, I don't need it. VC is going to have a step function change. So what's going to change when I change VC? When I change VC, clearly I'm going to change theta. But notice I'm also going to change theta, and Q is going to change. So Q is a function of VC that's changing, and a function of theta that's changing. So note that Q equals Q of VC and of theta. It depends on both. So now I'm in a situation f of xy. F is Q, x is VC, and y is theta. So I need to rewrite this. I need to write this as Q. This is nonlinear. I need to linearize. I want to write this as Q of VC theta is equal to Q of VC t less than 0, theta t less than 0, plus dq d theta, dq d VC t less than 0 times VC minus VC t less than 0 plus dq d theta at t less than 0 times theta minus theta t less than 0. Zoom time. So that's nothing to sneeze at. Okay, so here we have the value is the value at t less than 0, f of x 0, 1, 0, plus the partial with respect to the first guy, partial with respect to VC at t less than 0 times VC prime, plus the partial of f with respect to the second guy, dq d theta t less than 0 times theta prime. This thing is theta prime, this thing is VC prime. And notice they add the change in VC in the linearized version is in a separate term from the change in theta. Unlike the real equation, where it's all gobbledygook, they're in the same term. The linearized version separates them out. So one of these derivatives is really easy. If I take the derivative of q with respect to theta, I just get this thing with a minus sign. So it's that. So this thing is that is minus the square brackets, where here's the square brackets. The derivative with respect to VC is a little more nastier. So that's just taking the derivative of a quotient. So I need the derivative of the quotient times theta Cn minus theta. So this thing is the derivative with respect to VC of that thing at t less than 0 times theta Cn. I forget what's subscript or what's superscript. Theta Cn minus theta. Minus theta. This is all evaluating at t less than 0. So this thing is that derivative, and this thing is that derivative. But now let's just put it all together. So I have d theta dt. D theta dt is equal to. I'm going to divide by rho v cv. So I've got theta in minus theta over tau. Why do I have over tau? Because I divide by rho cv. I'm going to assume that cp is cv. So the cp's cancel, the rho's cancel, and I have v over dp, which is 1 over tau. Plus q, where q, this is the exact, plus q of vc theta. And now I linearize. Theta dt is equal to theta in minus theta over tau. Plus q at t less than 0. Plus q dvc at t less than 0 times vc prime. Plus dq d theta at t less than 0 times theta prime. Is that clear? Here's the exact. I just rewrote this equation, and of course I forgot to divide by rho vc. This whole thing is divided by rho vc. So I just took this equation and divided by rho vcv. I wrote it here. And now I linearized q because it was nonlinear by copying this. And now I'm going to take the exact for t less than 0. And that's d theta t less than 0 dt is equal to theta in t less than 0 minus theta t less than 0 divided by tau plus q of vc theta t less than 0 over rho v cv. So it's exactly what I did before, but now I have 3 terms for linearization rather than 2, because I have 2 variables, and I have to use these 3 terms instead of just these 2. And now I subtract these. I subtract them. And if I subtract them again, I have theta minus theta t less than 0, the theta prime dt is equal to theta in minus theta in t less than 0, theta in prime minus theta prime over tau. And now again, this cancels this. It's the same term. So now I have the q dvc at t less than 0 dc prime plus dq d theta t less than 0 theta prime. All of that divided by rho vc. Clear the same steps. Exact, linearized, exact for t less than 0, subtract. And now I've got a theta prime here, here, and here. I'll bring them all to the other side of the equation. The theta prime dt plus theta prime times. Well, here I've got 1 over tau, and then I've got a minus dq d, I can read my own handwriting here, dq d theta, and t less than 0 times theta prime. 1 over rho dc is equal to theta in prime over tau plus d theta dvc dc. And in this problem, so this is exactly of the form we're used to. We're used to the theta prime dt is equal to theta prime plus times something. ddt plus times constant is equal to something that's only a function of time. This thing. In the problem we stated, there's no change in theta in prime. The only change is in VCN. So if there were one, we know how to handle it. But what we assumed is that this is 0. We didn't have to, but we assumed it was 0. We assumed this is the only change. So this thing now is 1 over t. And I'm exactly of this form. Exactly of this form with constants. So I know the solution. I know that theta prime is equal to, again, theta prime of 0 is 0 because it's a prime quantity. And I just have b over a the theta dvc, I'm sorry, the q dvc, the q dvc t less than 0, dc prime, b over a is, so times t, times 1 minus e to the minus t. There I have my solution. And my kp is theta prime of infinity over dc prime of infinity is equal to dq dvc at t less than 0 times t. Okay, so I'm a couple of minutes over, but let's see where we are. We basically did 3 problems today illustrating linearization. 2 where we just had 1 variable and 1 where we had 2 variables. The algebra was more involved in this one, but the concept was the same. We write out the exact equation, we identify what's nonlinear. We linearize it, and then we write out the exact equation for t less than 0. We subtract this minus this, and we get an equation that always ends up being of this form. It doesn't have to be of the form where a and b are constants. Those are the examples we've done so far. Notice we can also handle step changes in both of these at the same time, or at different times, because we already have this equation. Are there any questions? Okay. There's only a little bit more left to chapter 3. I'm going to give you more homework on chapter 3. And we'll have an exam on all the materials in chapter 1, 2, and 3, but that's not going to happen for another more than a week from now, probably the week after next sometime. So, because I want you to have time to do the homework, digest it, and ask questions about the homework before the exam. Are there any questions?